Children, I hope you have gone through my previous videos and done all the work that was assigned to you. Let us now proceed further. Children, today we are going to start a new chapter, hydrocarbons. Hydrocarbons are compounds which contain only carbon and hydrogen. Now first we begin with the classification of hydrocarbons. On the basis of type of carbon-carbon bond present, hydrocarbons are classified into three main categories, that is saturated hydrocarbons, unsaturated hydrocarbons and aromatic hydrocarbons. First is saturated hydrocarbons. In saturated hydrocarbons, all carbon-carbon bonds present are single bonded. Now they are of two types. Open chain saturated hydrocarbons, they are also called as alkanes. Now they have open chain of carbon atom with single bond, like you see CH4, CH3, CH3. Okay, straight chain, and in between the carbon-carbon there is a single bond. So methane, ethane, propane, butane, they are all alkanes. Second category is cycloalkanes or alicyclic hydrocarbons. They are also called as cycloparaffins. Now the carbon atoms form a closed chain or a ring, but all the carbon-carbon atoms bonds are single bond. See here, this is a single. This forms a triangle, forms a square or a rectangle, quadrilateral. Then this forms a pentagonal structure, hexagonal structure. But there is only a single bond between all the carbons. So cyclopropane, cyclobutane, if it is having 4 carbons. If it has 5 carbons, it is called cyclopentane. If 6, cyclohexane, and so on. The prefix cyclo is added because it is a closed structure. Okay. Second category of hydrocarbons, it is called as unsaturated hydrocarbons. Now in unsaturated hydrocarbons, they contain carbon-carbon multiple bond. There can be a double bond or a triple bond, or it can have both double and triple bond. Okay, now in this, the first category is alkenes. Alkenes are open chain hydrocarbons having one carbon-carbon double bond. Alright, like see over here, CH2 double bond CH2. This is ethene. CH3 CH double bond CH2. So there is a double bond, so it becomes an alkene. Propene, 3 carbons, so propene. Alright, next is alkynes. Open chain unsaturated hydrocarbons having at least one carbon-carbon triple bond. So CH triple bond CH, ethyne, because 2 carbons, so eth, and CH3 CH, propyne. And next is cycloalkenes. These are ring structures having carbon-carbon double bond. So closed structures which have a carbon-carbon double bond, like in this case, see, 3 carbon are there, but this carbon is bonded with a double bond to this. So it becomes cyclopropene. If they were all single bond, they were cyclopropane, but now because of the double bond, the term here becomes cyclopropene. Same way over here, 4 carbons, there is a double bond, so it is cyclobutene. Alright, so these are called as cycloalkenes. Similarly, we have cycloalkynes. There is a carbon-carbon triple bond present in this. So it has 6 carbons ring, but these 2 carbons, they are linked by a triple bond, so it is called as cyclohexane. Next category is aromatic hydrocarbons, which are also called as arenes. Benzene and its hydrocarbon derivatives, they are called as aromatic hydrocarbons. Now you know benzene, it has alternate double bond and single bond. That can also be represented by a circle in between. And when any side chain is attached to the benzene ring, then also it will come under the category of aromatic hydrocarbons like toluene. Alright, it is known as methyl benzene. Can also be chlorobenzene, bromobenzene. All will come under the category of aromatic hydrocarbons. Now we first study about aliphatic hydrocarbons. In that also we will today we'll study only about alkanes. Now alkanes are called as paraffins because they are relatively unreactive substances. They have a general formula CnH2n plus 2, where N is 1, 2, 3, etc. Alright. Now nomenclature of alkanes we have already discussed in the previous chapter. Ane is added and methane, ethane, all that we did in the previous chapter of organic chemistry. Isomerism in alkanes also we have studied in the previous chapter. Now chain or nuclear isomers, structural isomers that differ in the chain of carbon atom are called chain isomers. Like butane has 2 chain isomers and pentane has 3 chain isomers, whereas hexane has 5 chain isomers. Now alkanes do not have position isomerism. So 2-methylpentane and 3-methylpentane are chain isomers. Alkanes which have 7 or more carbon atoms show optical isomerism. If they have 7 or more carbon atoms, then they will show optical isomerism. Okay. Now conformation of alkanes has been removed from your syllabus this year. We'll move on to the methods of preparation of alkanes. Now first method is from unsaturated hydrocarbons. But you know what is unsaturated hydrocarbon? Which have a double or a triple bond. So dihydrogen gas, H2 gas, gets added to alkenes or alkynes in presence of finely divided catalyst like platinum, palladium or nickel to form alkanes. This is called as hydrogenation because hydrogen is getting added. And this occurs at room temperature. See, CH2 double bond CH2, ethene plus hydrogen in presence of platinum or palladium or nickel gives you ethane. Same way, CH3C triple bond CH, this is propine. To this 2H2 will be added in presence of platinum, palladium or nickel to give you CH3, CH2, CH3. You will get propane from propine. Alright. This is the reaction. Then this second reaction in the presence of nickel catalyst at 523 to 573 Kelvin, you can get alkane like CH3CH double bond CH2. This is propene plus hydrogen. It will give you propane. This reaction is called Sabatier and Senderen's reaction. Next method of preparation is from alkyl halides. Alkyl halides except fluorides on reduction with zinc and dilute HCl give alkanes. CH3Cl, this is methyl chloride plus hydrogen in presence of zinc and HCl gives you CH4 plus HCl. Similarly, CH3, CH2, CH2Cl, propyl chloride plus H2 gives you CH3, CH2, CH3, propane plus HCl. Okay. So you can use any halide. We have used chloride over here. Only fluorides are not used. Alright, second is alkyl fluorides on treatment with sodium metal in dry ether give higher alkane. This is known as Wood's reaction. Now it is used for preparation of higher alkanes containing even number of carbon atoms. See, C2H5Br, C2H5Br. Two molecules we have taken in presence of 2Na and dry ether. You will get C2H5, C2H5. That is, you are getting butane plus 2 NaBr. But the thing is that with this method, Wood's reaction, you can prepare only alkanes which are having even number of carbon atoms. Okay, and if two different alkyl halides are used, then a mixture of the three alkanes is produced. Now from carboxylic acid. Next method of preparation. Now from carboxylic acids, you can prepare alkanes by three methods. First is decarboxylation. Decarboxylation means removal of CO2. So see RCOONA plus NaOH in presence of calcium oxide, and on heating it gives you RH plus Na2CO3. Like for example CH3COONA, sodium acetate plus NaOH in presence of calcium oxide, and on heating gives you methane CH4 plus Na2CO3. Okay. Next is like in this case, in the above case, calcium oxide keeps NaOH dry. Alright. Because otherwise NaOH will react with water. So it ensures complete decarboxylation of the acid. The next method is Kolbe's electrolytic method. Now in this, RCOONA plus water on electrolysis gives you RR plus 2CO2 plus 2NaOH plus H2. Like for example, if you take two molecules of sodium acetate CH3COONA plus 2H2 on electrolysis, it will give you CH3CH3, that is ethane plus 2CO2 plus NaOH, 2NaOH plus H2. What is the reaction that is taking place? At anode, two molecules of CH3COO minus, they get converted into 2CH3COO. They accept 2 electrons and then they get converted into 2CH3, that is C2H6 plus 2CO2. Alright, so you get ethane. At cathode, water molecule accepts the electrons which are released over here and gets converted into OH minus plus H plus, and this 2H plus, they form H2. Alright. So this was O minus initially, it had 1 electron extra. It will release those electrons, get converted into CH3COO, which in turn gets converted into ethane plus 2CO2. Now next is, this was about the Kolbe's electrolytic method. Next is reduction of alcohols and aldehyde. Now alcohol and aldehyde, they get reduced in presence of, alcohol gets reduced in presence of red phosphorus at 423 Kelvin. So ROH, that can be any alcohol, plus 2HI will give you RH plus H2O plus I2. For example, CH3OH, methyl alcohol plus HI, 2HI gives you CH4 plus H2O plus I2. Similarly, aldehyde RCHO plus 4HI in presence of red phosphorus and at 423 Kelvin gives you RCH3 plus H2O plus 2I2. For example, CH3CHO, acetaldehyde plus 4HI will give you CH3CH3, that is ethane plus H2O plus 2I2. Okay, so in this way alcohols and aldehydes can get reduced to give you alkanes. Aldehydes and ketones on reduction with amalgated zinc and concentrated HCl also give alkanes. This is known as Clemmensen reduction. For example, see CH3CHO plus 4H in presence of zinc amalgam. solution. So ZnHg and concentrated HCl on heating. They give you CH3 plus H2O. Similarly, CH3CO, CH3. This is acetone on plus 4H in presence of ZnHg and concentrated HCl. On heating, it gives you CH3, CH2, CH3, that is propane, plus H2O. Alright, so this is propanol. Acetone is getting, in first case, aldehyde is getting converted into alkane, and in the second case, ketone is getting reduced to alkane. But this reaction takes place in presence of zinc amalgam. That means zinc and mercury and concentrated HCl. Now next is preparation of alkanes from Grignard's reagent. Grignard reagent, you know the formula is RMgX. Now RMgX plus HOH, that is water, gives you RH plus MgOH(X). Like if you take C2H5MgBr plus water, it will give you C2H6 plus MgOH(Br). Alright. Alcohols also can react with Grignard reagent. RMgX plus C2H5OH will give you RH plus MgOC2H5. Alright. Then RMgX can react with ammonia as well. Plus NH3, it will give you RH plus MgNH2X. So in this way, from Grignard's reagent, by reacting with water, alcohol or ammonia, you can get alkane, corresponding alkane. Now next we come to the physical properties. First four members, C1 and C4 are gases, C5 and C17 are liquids, and alkanes containing 18 or more carbon atoms are solid at 298 Kelvin. They are colorless, odorless. Boiling point of straight chain alkane increases with increase in their molecular mass because van der Waals force of attraction increases with increase in size and surface area of molecule. Among isomeric alkanes, the boiling point of branched chain isomer is lower than normal alkane. Greater the branching, lower is the boiling point due to decrease in surface area and van der Waals force of attraction among their molecules. Melting point of alkane increases with increase in molecular mass, and alkanes, normal alkanes with even number of carbon atoms have lesser melting point than normal alkane with odd number of carbon atoms. The density of alkane increases in molecular mass till limiting value of 0.8 gram per centimeter cube is reached. Okay, so these are the physical properties of alkanes. Next we come to the chemical properties. First chemical properties is combustion. Alkanes can burn with oxygen, like CH4 plus 2O2, it gives you CO2 plus 2H2O. The general combustion equation is CnH2n plus 2. This is the general formula of alkanes, plus 3n plus 1 upon 2O2. Okay, so like in this case, CH4, n was 1. So 3 plus 1, 4 upon 2. So we took 2O2. It will give you NCO2 plus n plus 1 H2O. Incomplete combustion of alkane gives carbon black. Like if CH4 is burnt only with O2 instead of burning it with 2O2, incomplete combustion will take place and it will give you C plus 2H2O. Okay, next property is oxidation property. Controlled oxidation. Alkane gives a variety of oxidation products. See, first is CH4 plus O2 in presence of copper at 523 Kelvin temperature and 100 atmosphere pressure. It gives you 2CH3OH, methanol or methyl alcohol. Then CH4 plus O2 in presence of MO2O3, molybdenum oxide, gives on heating it gives you methanol, HCHO, aldehyde, okay, plus H2O. Then 2CH3CH3 plus 3O2, ethane plus oxygen in presence of manganese acetate, CH3COO whole twice Mn, on heating gives you 2CH3COOH plus 2H2O, ethanoic acid or acetic acid as we commonly call it. Then CH3 whole thrice CH, 2-methyl propane, when treated with KMnO4, it gives you CH3 whole thrice COH, 2-methyl propane 2 all. Alright, so a number of products. You get alcohol, you can get aldehyde, you can get carboxylic acids if you change the conditions of oxidation. Next is substitution reactions. In substitution reaction, first is halogenation. Methane, when it reacts with chlorine in presence of sunlight, it gives you CH3Cl plus HCl. Further reacting with Cl2, it gives you CH2Cl2 plus HCl. Then CH2Cl2 plus Cl2 gives you CHCl3 plus HCl. CHCl3 plus Cl2 gives CCl4 plus HCl. So you get chloromethane, dichloromethane, trichloromethane and tetrachloromethane. Similarly, ethane, CH3CH3 plus Cl2 will give you CH3CH2Cl plus HCl. Chloroethane. Rate of replacement of hydrogen of alkanes is 3 degree is greater than 2 degree, which is greater than 1 degree. Alright. It is found that rate of reaction of alkanes with hydrogen is that fluorine is highly reactive, then chlorine, then bromine, and the least reactive is iodine. Fluorination is a violent reaction, but iodination is very slow and a reversible reaction, and it can be carried out in presence of oxidizing agents like HiO3 or HNO3. So then the reaction becomes CH4 plus I2 gives you CH3I plus HI, because this is a reversible reaction. So HiO, in presence of HiO3, when if you carry out this reaction, then HiO3 will combine with 5 molecules of Hi to give you 3I2 plus 3H2O, and then the reaction will proceed only in forward direction. Next substitution reaction is isomerization reaction. Now in isomerization reaction, see, CH3 CH2 whole 4 CH3 in presence of anhydrous AlCl3 or HCl gives you, this was normal, you started with normal hexane. When you treat it with anhydrous AlCl3 or HCl, you get CH3CH, CH2 whole twice CH3, and here CH3. So this is 2-methyl pentane plus, this time the attachment will be on the third one, then becomes 3-methyl pentane. So you get two types of pentane, 2-methyl pentane where CH3 is attached to the second carbon, and 3-methyl pentane where CH3 is attached to third carbon. So you are getting isomeric forms. This type of reaction is called as isomerization reaction. Next reaction is aromatization reaction. Aromatization reaction, normal alkane having 6 or more carbon atoms on heating to 773 Kelvin at 10 to 20 atmospheric pressure in presence of oxides of vanadium, molybdenum or chromium. supported over alumina get dehydrogenated to give benzene and its homologues. This is called aromatization or reforming. Like you have taken normal hexane over here. See, it is not joint over, it is a straight chain, normal hexane. When you treat it in presence of these catalysts, chromium or vanadium or molybdenum, alright, oxides, at 773 Kelvin or 10 to 20 atmosphere pressure, it gets converted into a closed chain structure, that is benzene plus 4H2. So aromatic hydrocarbon has been formed. So this reaction is called as aromatization. Next is reaction with steam. Methane reacts with water in presence of nickel and on heating, because it has to be steam, not normal water. So it gives you CO plus 3H2. Next is pyrolysis. Higher alkanes on heating to high temperature decompose into lower alkanes or alkenes. Such a decomposition reaction into smaller fragment by application of heat is called pyrolysis or cracking. Like C6H14 at 773 Kelvin. This is normal hexane. It will give you C6H12 plus H2 or C4H8 plus C2H6 or C3H6 plus C2H4 plus CH4. Similarly, dodecane C12H26 in presence of platinum, palladium or nickel at 973 Kelvin will give you heptane, pentene and other products. C7H16 plus C5H10 plus others also. So these type of reactions in which higher alkanes are breaking down into smaller alkanes or lower alkanes, that is called as pyrolysis. Next we come to the uses of alkanes. Methane is used to prepare carbon black, which is used to prepare black ink, printer ink, polish, paints, etc. LPG, liquefied petroleum gas, is a mixture of butane and isobutane, and it is used as domestic and industrial fuel. Alkanes are used for manufacture of alcohol, aldehydes and carboxylic acids, and higher alkanes are used as gasoline, diesel, kerosene, etc. So this is about the alkanes. We will do further in the next video.